Ripples in the fabric of space-time, black holes, neutron stars. Well, they all sound a bit sci-fi, which is why it's so refreshing to find that in fact they're not. And to prove that, we're talking to a Otago professor in applied mathematics, Jorg Frauendiener. Hi there, Jorg, how are you?
Okay.
Well, I guess the first thing I'd like to ask really is, what is a ripple in the fabric of space-time? It's the sort of thing that you hear in Star Trek, but what is it?
Well, that's, as I said before, that's already the one of the most difficult questions that you can ask in that area. But a very vague analogy is when you look at the surface of a lake, and you throw a stone into the lake, and then you see the waves moving away from that impact of the stone, and then you see these ripples. That's exactly the picture that you should have in mind when you think of the ripples in space-time. It's not only a surface, a two-dimensional thing, but it's a four-dimensional thing. But that's the analogy that you have to keep in mind.
That's pretty freaky.
If you say so, yes.
Well, I guess it's that sense that you can alter time really through gravity is also kind of freaky, because that's sort of kind of what it's about, isn't it, to some extent?
Yes, to a certain extent. The theory of Einstein about the gravitation tells you that when you have a huge chunk of mass, which is really huge, then the course of time is altered close to that body, compared to clocks which are far away from that body. So they tend to go slower and slower.
So it's just a short step from there to wormholes and travelling in time. And
yeah, the step is really just increasing the mass of that body. As soon as this mass of the body reaches a certain value, then you get a collapse of this body, shrinking down to an infinitesimal object. You get a creation of a black hole, or depending on how you do this, of a wormhole and these kind of things.
So in theory, a type of time travel is kind of possible.
That's a very vague thing. Mathematically, you can write down systems where you do see time travel things. But if you try to build these things in the laboratory, you will have a lot of problems, because this is what people call exotic matters, which you don't produce in a laboratory. So it's mathematically possible, but physically I doubt it.
Well, it's very hard to build a lab big enough really to get a very large object.
That's with ordinary matter, you have to have a huge laboratory. With these exotic types of matters, you can have very, very small things, but they are very, very heavy.
Okay, so why do you study the ripples and fabric of space-time? Why do you study that, and how do you study that?
Well, really, it was what you said in the beginning. It's a fascinating thing that clock or time and length can be altered, and that was something that interested me right from my high school days. And I always wanted to go into that area, and so that's here I am.
And so how do we measure those ripples? Because obviously they'll be a very long way away.
So these ripples are really ripples in the space-time, and when a ripple passes you can detect this in the when you compare different lengths. So currently we have detectors which have been built in the US, in Europe there are two. There might be one coming up in Australia. That's an effort that they are doing there, and these are interferometers. So these are they have two arms, and laser light reflected between those two arms. And when one of these ripples goes through, you can see this the arm length changes in a very specific synchronous way, and you can measure this by looking at optical measurements and things. And so the current efforts are to really see these ripples directly. We have not seen them so far, but we are quite confident that within the next 5 to 10 years we will see them, because the technology used in these detecting machines is getting better and better, and the time scale is that within 5 years we should see something. If we don't see something, then we have to go back and think about the theory again.
So if we haven't actually seen them, are we sure that they are in fact there? How do we know that?
We have indirect clues that they really do exist. So there are, this comes from observations, astrophysical observations. There are systems of two stars which are very close to each other, and they circle around each other. And what one observes is that the period with which they circle around each other decreases.
Yes.
So this means that they are circling around each other faster and faster. And the explanation for this is that the system loses energy due to these gravitational waves, which produce the ripples in the space-time. And that causes them, because they lose energy, they shrink together, but angular momentum is conserved. So that's a theorem from classical physics. So that means that, like an ice skater, when she pulls in her arms, she tends to spin much faster.
Okay.
And that's what these systems also do. They tend to spin much faster and faster, but coming closer and closer together. And we see this. We see the decrease in the period, and the only explanation that we have so far is that they really lose energy due to the gravitational radiation, and that is an indirect proof for the existence of these things.
So what sort of, is it a type of geometry, or what sort of math do you use when you study these ripples?
Yeah, it is a type of geometry. It's called differential geometry, and in particular, in that area, it's what's called Lorentzian geometry. It's not the standard differential geometry that pure mathematicians use. It's a more adapted version of differential geometry, which is used in mathematical physics. It was developed exactly for this type of phenomena.
And do you use numerical simulations? You're doing a lot of sort of number crunching on computers. Is that
that's something that has really started only compared to the whole development of the area just recently. There have been huge efforts in producing numerical codes which compute these the exact shape and properties of the ripples that come off one of these binary systems that I explained earlier. But really the interesting thing about this area is that it's really not only numerical work, there is a lot of mathematical work also involved in it. And since we have these experiments, the detectors, there's a lot of laser technology and physics, laser physics, vacuum physics. It's an area which is really very cross-disciplinary.
So that means you interact with these other people, the physicists and this one and that one quite a lot?
Yeah.
And you can all speak the same language, as it were, through math? Or
well, basically we speak the same language. So within that area, you know what a Riemann tensor means, you know what covariant derivative and these kind of things mean. And I think that's across the board of all the disciplines that are involved in this.
And do you find that they're all mostly sci-fi fans as well that are involved in this area?
I think, probably yes, because I think a big motivation for people to go into that area is from sci-fi. You see Star Trek, you see the what is it called, the warp drive?
Yes, the warp drive. Yeah,
these kind of things. There has been, there is a mathematical model for the warp drive within that, within that theory.
Yes,
and
just get enough of that dark matter or something.
Yeah, exactly. But that's one of these exotic matters that I was talking about. We don't really know what it is.
And that big new collider they've got in Europe, that's part of what they're doing, is producing.
Well, that's
well, they're looking at the very basics.
That's particle physics,
yes.
And they are looking at really the very, very small scales and look at what the matter is made up of.
Find that ultimate building block.
Exactly,
type of stuff.
and we will see how that goes. Yeah,
but they can also produce dark matter.
No,
through that
no. They are hoping to produce something that then can be explained as being the dark matter.
Oh, okay.
But they don't know what it is. So
yes.
They are looking for something that they don't really know what it is.
Is that something you find quite interesting? Is that often you're looking for things you don't really know about?
That's what the fun is about.
Yeah, the journey of it and the creativity.
Yeah, that's what research is about. You have a certain idea about what you want to do, but you don't know exactly what will come out of it, or whether this idea actually is a useful one or not. So I think that's a big chunk of why research is interesting and why people are doing research, because they are curious to see what happens if I do this.
Oh, it's fascinating to talk to you today, Jorg. It's been absolutely wonderful. So thanks for your time.
Thank you.